Hi guys, I am Agnish. I live in Kolkata in India, and I've basically come to Token2049. So I've been working on this project called TrueZK, but I'll come to that later. This talk is more about Verkle tries. Currently, I'm a protocol fellow at Ethereum Foundation under the EPF program, and I've been recently awarded the Ethereum Dev Connect scholarship. So I'll be going to Istanbul if anyone wants to meet me there. Okay, so basically, I'm gonna break it down. So yeah, okay, cool. So before we understand Verkle trees, we need to understand the difference between vector commitments and hash functions, how they are different, and how basically Verkle trees, how I'll build it up, like how Verkle trees are basically faster and more efficient. So yeah, so verifying data via hash functions basically results in revealing the whole data. Yeah. But if I use vector commitments, which is again, it's like based on the concept of polynomial commitment schemes, we can basically simply prove things like, suppose I have an array and I want to prove that the second index of this vector is indeed 72. Then the verification just happens by making an opening at that point, eventually verifying that point. Yeah, so this is basically like a visual representation. You have an array, the second one is 72. What you do is basically make a commitment of the fact that the second index is 72. And from the verifier side, you have an opening. You'll just have 72, and you are able to verify that the second index is indeed 72. But if you used a hash function, you would probably have to take out like that entire blue chunk. So there's no there's no perk. Like we are basically revealing the entire data set, like vector. So yeah. So primarily that's the downside of using the hash function. As I showed you, you're taking the entire array. So that is something we do currently in Merkle proofs, because when we are constructing, so when we want to basically check or something like that, we are basically considering all of the sister nodes of the data, and we are basically aggregating sister nodes, all of the sister nodes, and finally the final Merkle proof. So in the final Merkle proof, there is data of all of the sister nodes, which is probably there can be a better solution to that. So in Verkle trees, we basically, since we use vector commitments, it's pretty much like this. This is actually stolen from Vitalik's blog. So yeah. So yeah, we want to prove this. So we have aggregated proofs. Yeah. So and it's mainly path dependent. It's not dependent upon the sister node data. So we can ignore that. So no sister node. Okay, system nodes are indeed needed in the proof. The proof generation takes a more path-specific approach. They link each commitment and the path to the next. Okay. Advantages. This is the advantage. The lead. So both of the tries, specifics in each proof. For Merkle tries, leaf data plus 15 siblings, 32 bytes for each level, around 7 levels. Proof size is 3.5 MB for 1,000 leaves, whereas for Verkle try, we have the leaf data, we have the polynomial commitments, values, plus index of the child, which is 32 bytes, 1 byte small constant size data. Okay. Usually we have 4 levels, and the final proof size is boiled down to 150 KB, which is a substantial decrease in the proof size. Merkle Patricia tries are primarily based on collision-resistant hash functions. However, for Verkle try, we had two mathematical approaches. For the first one, for the each one state, we had KZG polynomial commitments based on bilinear pairings with the BLS 12381 curve. And we did need a trusted setup for this, since we are using bilinear pairings. And now for ETH2, we have basically IPA plus Peterson commitments with the Bandersnatch or the Banderwagon curve, which is basically an improvement on Jub, if you're aware. Yeah. So Verkle tries plus the Verkle cryptography API is pretty much most of the thing about the Verkle library. So the trie structure plus the cryptography API. So initial mathematical approach was using multi-point proofs based on KZG polynomial commitment schemes for the Verkle trie of depth, say D. So yeah, we could compute a commitment to individual vector at each level. So A0, A1 up to A2 to the power D minus 1, which is basically like, you'll know if you, like, it's like tree height kind of data structures and algorithms. So where the definition of the polynomial commitment is Px, okay, this is basically like the formula. If you're interested, you can read more about it. Commitment sizes are usually 48 bytes long, and they're computed on the BLS12381 curve. Again, if you know this curve. Okay. Demerits of this approach is as, yeah, pairing-based cryptography needed a trusted setup, which was implemented by secure multi-party computation. Trusted setup usually takes time. And on the other hand, we have inner product arguments, kind of like taking the bulletproof approach, and Peterson commitments, which were mainly based on the discrete log problem, and it does not require a trusted setup. So basically, executing these Verkle proofs will be much faster. Yep. A few more things on Peterson commitments if you, again, are not interested. So yeah, anyway, we can just skip it if you want to. Because, like, yeah, this is just basically a different mathematical tool which you may or may not want to, like, right now know. Yeah. Okay, so there's just one very good property. Peterson commitments are basically homomorphic in nature, which basically means for like, if we are basically performing a commitment for M1 R1, which is basically, suppose you can think of it as a key value, and again M2 R2, then if you add it up, then the final commitment is sort of homomorphic in nature, so that it will be equal to the commitment of M1 plus M2 and R1 plus R2. This actually gives us a very good leverage to do multi-point vector commitments, thereby making the Verkle proofs mainly path dependent and not dependent upon the sister nodes. So just a quick recap. Verkle uses commitments, so most of the data isn't revealed. Verkle cares about path, not siblings, so smaller proofs. Verkle cares about data, depth, so more children means lower depth, which means more data aggregated into a single proof, which again means smaller proof. And this is one more feature in the Verkle spec, that account and storage tries are merged into one, hence again a much smaller proof. Why can't we use a single commitment? Because getting a vector commitment for the whole state kind of makes the proof generation very latent. We usually make a trade-off between proof size and computation time. Ideally, like, Verkle tries are like 4-level deep and contains around 256 children. So yeah. Statelessness. Yeah, this is like some of the features that Ethereum has been working on, but again, most of the specs and most of the implementation hasn't been done yet. So yeah, but these are the main features. So reduced amount of data to participate in the network, easy and less time-consuming network syncing, lesser baseline for storage specs, reduced amount of data required to process, which shall be easier for smaller devices to become a client or something, faster access to information, because again, we are reducing proof sizes and so many things. So this is the problem for state, this is a new feature, we call the state expiry. So every year, the period resets with a new tree. So the data for the current and the previous year is stored, and the data for the previous years are kind of discarded except for the state roots. And if you want to access the data before 2 periods, we need something called data resurrection, and we need a valid proof for that as well. So suppose, like, you have period 0, you have tree like this. Okay, once period 0 is over, you freeze this, and then you again have a period 1 tree. Yep. Oh, you have another period 1 tree for this. And now we basically need to ensure that nothing of, like, let's suppose, so this is 0, 1, 2, right? We need to ensure, suppose this is period 1, 2, and 3. So I need to ensure that nothing of period 0 is resurrected into period 1. And only then, if we are basically creating a new tree for period 2, and we want to resurrect something from period 0, we just pass the state root and the proof. And we'll be able to access the state root of period 0 as well. This is the third feature for the Verge upgrade, that is address space extension. Increasing the number of bytes in an address from 20 to 32. Use bytes 3 and 5, 3 to 5 for the period which they belong at which the address was first accessed. Actually, yeah, which the address was first accessed. Using bytes 6 to 31, that's 26 bytes to store the hash of the public key. Use byte 0 for version, and bytes 1 and 2 are reserved, maybe like for later purposes, future use. So this is kind of the thing. So for period 0, this address, let's suppose this has a balance of 1, 2, 3, 4. Period 1, it will just change to 1. Period 2, it will change to 2. And if I want to resurrect something from period 0 again, then again it will get reset to 0, 0, 0, 0, all of that. Okay. Connecting address space extension with state expiry, simplifying data storage by subdividing state tries into periods, charging. Okay, so basically, if we are subdividing state tries into periods, then there can be several node operators who can charge for data storage in exchange of a fee. So if you want to resurrect something from period 0, you might want to, like, the operator who is running the node may want to charge a fee from you. Yeah. There is one potential threat though, so breaking existing contracts. So the Epsilon team is working on something called contract bridging to basically mitigate that threat. State networks, this is again a completely new approach by Piper. Piper used to be one of the former program managers for EPF. It states that a node stores only a subset of the entire data. Data is requested over the network as per need. So maybe someone would be a data storage operator. I would have just a subset of the entire data. If I would need, I would basically ask, like, hey, can you do this? And that guy would probably charge some fee for sending over the data. Proofs provided to ensure that the provided data is correct. Yeah, definitely, that needs to be there as well. Pros is be a validator in each2 without storing any data at all, because in real time you can pretty much ask for like other operators for the data. Yeah. And yeah, this is some of the existing research going on in EPF. That's something I've been currently working on. One is the Verkle try library and migration to Verkle trees with the existing ETH1 and ETH2 Nimbus client. So one for the execution and one for the consensus client. Using the Constantine crypto library written in NIM, you can check that out. It's linked. I can share the slides. Yeah, it's in GitHub. The second one is Verkle try library for Besu. Currently interfacing Arcworks. Yeah, we are interfacing Arcworks, but again, what I feel is, again, I have been discussing this with a lot of people lately, that the Verkle try crypto library is pretty big and interfacing is pretty complicated and painful. So some potential explorations can be exploring the need for developing a Java cryptographic primitives library, which would be compatible with the Verge, which would have the new curves and everything. And possible changes in type 1 Ethereum equivalent ZK rollups. Why? Because when Verkle tries and the Verge kicks into mainnet, a lot of the execution specs are going to change. So to keep up with that, we need to have Verkle try libraries in like sort of ZK snark frameworks like Halo 2, so that type 1 ZK rollups can sort of keep up with the Verge upgrade. And that is it. That is pretty much it. Yep. Thank you. Oh yeah, any questions?
What are your questions, ladies and gentlemen?
When it's possible to get the presentation?
Yeah, I'll send it over. Okay, I can. Yes.
So RPA versus KZG, the KZG has constant size openings and commitments. So whereas I think IPA plus Peterson has
Fact.
logarithmic sized openings.
Yeah.
So can you dive a bit about why do you use IPA plus Peterson?
I haven't used anything. I mean, yeah, this is a question actually. Like, I haven't really found any documentation over it. I have asked a lot of people who are in Ethereum ecosystem as well, and the only thing that they have always told me is basically eradicating the need for a trusted setup.
Given that they already have a registered state one trusted setup, just research.
Uh, I I don't know. Like, basically, yeah. It's basically the Verkle spec. I'm following the Verkle spec. So,
I have the same questions. I thought maybe
so you didn't get any answer. I haven't got any answer either.
I asked Randall also.
You asked Dankrad. Okay. Okay. If he doesn't have an answer, nobody has. Anyway. Okay. Any other question? Okay. Okay, we can connect. Definitely. Yes. Thank you.